2 minutes over. We got about 16 people. I think we might see a little bit more coming in. So with that, I would love to introduce Shumon, and Shumon can speak Bengali as well. So
yes.
যদি বাংলায় কথা বলতে চাও বাংলায় কথা বলতে পারো. Shumon is one of the super asset of AWS and Amazon. He's going to introduce himself. He's here for a very long time. He's a machine learning expert. If you have any question, he's in মানে সে আমাদের ইয়েতেও আছে, Slack channelও আছে. So if you need to ask him any question, you can ask him any question in future, like any of the mentoring group as well. So again, he's in the Slack channel. You can Slack him directly. আজকের যেটা হবে একটা চমৎকার একটা টপিক, এটা মেশিন লার্নিং স্পেসিফিক টপিক। এন্ড আজকের সেশনটা শেষ হলে তোমাদের অনেককেই আমি কিছু কুপন দিছি যাদের নিজস্ব অ্যাকাউন্ট আছে। আর আজকে সেশনটা শেষ হলে তোমরা যারা যারা চাও ওই আমি লিংকটা দিয়ে দিচ্ছি, সেখানে তোমাদের নাম দিলে আমরা ইভেন্ট ইঞ্জিন তোমাকে দিয়ে দিব। ইউ ক্যান চেক আউট আওয়ার SageMaker, some of the things that Shumon is going to talk about, you can look at up, or you can just test out the SageMaker. Pin posted দেওয়া আছে already, কি কি জিনিস তোমরা চেক করতে পারো, টেস্ট করতে পারো, get your hands dirty essentially. So at the end of the session, maybe 10 minutes prior to the session, you should do that. আরেকটা জিনিস আমি তোমাদেরকে হাইলি রেকমেন্ড করব, যেটা এর আগের দিন রেকমেন্ড করছিলাম, আজকে এখন আমাদের হয়তো 19 জন আছে, আরো জয়েন করবে ইনশাআল্লাহ। কিন্তু আমি আশা করতেছি তোমরা প্রত্যেকে ওই গতবার যেভাবে তোমরা লিঙ্কডইনে পোস্ট করছিলা, সেম থিং প্লিজ পোস্ট, বিকজ দিস হেল্পস, আমাদেরকেও হেল্প করে, আবার তোমরা অন্য একজন আরেকজনকে ইন্সপায়ার করতে পারো। সো উইথ দ্যাট, what I was going to ask you to do, let me go to the gallery mode and come to the camera and let me take a quick picture. তোমরা একটু ক্যামেরাতে চলে আসো. So I just wanted to take a quick picture and then we'll start. Thank you for coming. Thank you for coming. Yes. Almost everybody. Few more. চলে আসো. মৃদুল, মাঝারুল, তোমরাও চলে আসো. Sudeep, Shamima, Nahid. Almost there. Aditya is here as well. So fantastic. We got a lot of great people. Abdullah. Okay, good. Whoever is here, I'm just going to take a picture. I don't want to take too much time out of it. So তোমরা সবাই সবার পিকচার নিয়ে নাও এখানে, and then post the similar thing that আমরা যে পোস্ট করছিলাম। হ্যাঁ, মনে আছে না যেভাবে আজকের ইয়াটার একটা সামারি, তোমাদের ফিলিং, just do it. Put it in LinkedIn. Make sure you can tag myself, Shumon, Aditya, whoever else, Lijan, Sid, Burak, all of them. So just do it. With that, I'm gonna hand it over to Shumon. And Shumon, if you don't mind, introduce yourself and go from there. It's all yours, my friend.
Sure. Thank you so much, Zaman. So, hello everyone. Good morning, good evening, depending on from where you have joined. It's such a pleasure to be here, and I think Zaman Bhai is very humbled enough to welcome me in this fashion. I'm not an expert of machine learning, but surely I focus on machine learning, and I started to work on machine learning since I joined AWS roughly around 1 year 9 months back, roughly around 2 years. It's been an amazing journey so far at Amazon, and prior to that I used to work for different companies. So I'm coming from a different background. I mostly work in the storage side. তো তোমরা যদি কোনোদিনও ইনফ্রাস্ট্রাকচারের দিকে কাজ করে থাকো, নেটওয়ার্কিং, স্টোরেজ সিস্টেমস, যদি AWS এ যেটা আমাদের EBS, যেটা আমাদের ইলাস্টিক ব্লক স্টোরেজ, তো আমি ওইটার ইঞ্জিনিয়ারিং টিমে ছিলাম অন্য কোম্পানিজে। So I spent roughly around 12-13 years on storage tool development and performance. And যখন আমি পারফরমেন্স টুল ডেভেলপমেন্ট করি, তখন অনেক রকমের ভিজুয়ালাইজেশন টুলস এক্সপ্লোর করি। তো তখন থেকে ইন্টারেস্ট ছিল মেশিন লার্নিং এ এক্সপ্লোর করা কিংবা অ্যাজ এ ক্যারিয়ার ওখানে মুভ করা। তো ওটাই ছিল মোটিভেশন। তারপরে I joined AWS, and after that this gave me a good platform where I can learn and do something meaningful for everyone. So that's how I started. And at present, I'm also pursuing my master's in machine learning, apart from my day-to-day work. And in Amazon, I work for developer relations team. So what we do essentially is we work with communities, and we work with all developers and students and engineers across the country. And when I say across the country, it's not only India. I kind of take care of India, Bangladesh, Nepal, and Sri Lanka predominantly. So many of you might know the AWS Bangladesh user group. Right? So I work with the user group leader like Tisha. You might know him, Abir, and so on. So this is my first time that I'm talking to you, and I'll make sure that I'll be consistent with this group, and I'll try to help you wherever I can. Even if I'm not the expert in all the areas, but I'll try to make sure that you get everything that you would need from AWS side. Zaman Bhai is already doing it a lot and driving this all. And I was fortunate enough, when he pinged me, I think couple of months back, but due to some other things, I could not able to come. It's my bad. But from now onwards, I'll make sure that we have a frequent discussion. It's not about only this event, but feel free to reach out to me after this event for anything around AWS or machine learning in specific. Okay, so that's about me. So what I'll do now is I'll share my screen. Okay, and what I will do is I will try to check the chat after some time, and then we will answer all the questions whatever we get. Okay, so I'm not in a hurry to complete the slide or demo whatever I have now in next 30-40 minutes or 1 hour, but the intent is whatever we learn in next 30-40 minutes, we have to make sure that we learn something substantial, so that you don't feel like you just wasted your evening. Okay, so it's not about that we have to complete something. If something gets little overwhelming, we will just stop there, and then we might have another session the next week. Okay, so it's not like a very formal kind of event where we have to complete something. Okay, so with that, let's get started. And Ami, but one thing is, don't call me sir, because that is very quite. It's very. It gives some kind of discomfort, and I feel very cautious about that. And I don't feel if I'm not a right person to get the sir title. So call me by my name. And I'm from Calcutta, basically, and I'm born and brought up there, and then I moved to Bangalore. And my parents and their family and all, they were from Bangladesh, as we all know. Right, half of the people in Calcutta are from Bangladesh. So I've been in Bangladesh last year for the AWS recap, and I had wonderful food. I bought fish, and then in the airport itself they blocked me, so I had to give that fish to the driver who came to drop me. And I just made sure that someone should eat that fish. It should not go in vain. And my dad was very disappointed because he was just eyeing for that Ilisha fish. So anyway, enough about blabbering. So I talk a lot, mostly things which are not needed. So please feel free to stop me whenever you feel like. Okay, so let me first share my screen. Okay, so can you see my screen now?
Yeah. Can you please start your recording?
Okay, so can I do that or?
I guess Jaman sir can do that. He's one of the hosts.
Anybody can. I mean, Shuman, you can do that. If you don't mind, just do a local, because I made him host.
Yeah.
Just do local recording. Don't do in the cloud. Last time we missed a lot of stuff.
Yeah, record in this computer, right?
Yeah. And then you can upload in Word docs. Send me the link. I'll upload in YouTube. Okay.
Perfect. Okay.
Thanks.
Awesome. Man. So before we get started, I know that a lot of people are from machine learning and data science background, but can you just give me some yes, no? How many of you have worked in machine learning or working in machine learning? Yes, no, that's all. I mean, just to get a feel of where we are, so that we can discuss something meaningful. Okay. Okay. Okay, great. So most of you, I guess I got a couple of response. Very nice. Okay, beginners. Okay, fantastic. The next question is, how many of you have heard about transformer and BERT or natural language processing, NLP? How many of you heard about that? It's not about you know that, but just heard about that. Excellent. Okay, and how many of you have worked on any of the NLP-based network or model like LSTM, RNN, or anything? Does this sound familiar to you? Have you ever worked on RNN, LSTM, or any of the NLP-based techniques? Okay, okay, Mridul, you have worked on it. Shamin also. Okay. Okay, Rafa Majumdar, you say no. You don't have to feel sad about it. Yeah, in a way, it's good because, in fact, I also do not know much about LSTM and RNN because when I started with Transformer itself because that's something that is legacy and we will discuss that now. We will, get there. Okay, I guess we are good. I got some idea about all of you and we'll have some questions at the end or the middle, depending on whenever we feel like. But feel free to stop me if you have any questions. Okay, so what we will do is today we are going to talk about transformer and BERT. Okay, so now what is transformer? What is BERT? And where all of this fit in? So basically, if you look at machine learning, there are different domains in machine learning, right? One is computer vision, then one is NLP. So these are like different areas. Like if you take a problem which is related to computer vision, then you will think about CNN or technology around the deep learning part, right? And when we talk about any natural language processing, or in other words, anything to do with language, right? Let's say Bangla to Hindi or Hindi to English, English to French, right? All of these are comes into natural language processing problems. Okay, a few other example would be in the phone itself. When we type, you might have seen, even you can try this out. You type a single word when you text a message to your friend. Automatically, the next word you get it right as a recommendation. If you just press or click on that, right, automatically you will get the next word. So it's kind of you get the full sentence auto completion. So these are the tasks which are performed by NLP based models. Okay, and in last 3 years, there has been a tremendous growth in this NLP field because of transformer and BERT. And whatever we are talking now, these are just 2-3 years old technology or the models or network, whatever you call it. And this is the right time to learn about it. So things used to work fine even before that, but those are not something that people are focusing on now because this has changed the whole dynamics of natural language processing tasks. Okay, these two things like transformer BERT and few other things that we will talk about today, they do not solve all the problems, but whichever problem they solve it in a much efficient and state-of-the-art way with respect to the previous models that we had like RNN, LSTM. Okay, so with that, let me go to the next slide. So why transformers? Okay, so few of you have already worked in RNNs or LSTM. So first place, transformer has come in, I guess, 2017 timeframe. Okay, 2017. So before that, we used to have different models or different technology like RNNs and LSTM. These are very old techniques to do machine translation, text generation, and next word prediction. Next word prediction is nothing but যেটা এখন just বললাম, যেটা তুমি SMS করছো, তুমি একটা word লিখছো, next word automatically predict হয়ে যাচ্ছে, right? তো এই সব প্রবলেমস গুলো RNN আর LSTM আগে এটা সলভ করতো। And এখন যারা এগুলো জানো তো খুব ভালো, যদি নাও জানো কোনো ব্যাপার না। তো এটা কিন্তু আমি এটার লিমিটেশনস গুলো বলছি, এটা কি মানে এটা কেন লোকেরা এখন আর ইউজ করতে চায় না, just because transformer has given them a lot of benefit. Okay, so one of the benefit is this. So in RNNs and LSTM, the way that it used to do any translation or anything of that sort is like this. So তুমি একটা সেন্টেন্স দেবে, ভেবে না এই সেন্টেন্সটাই what time is it, ওকে? তো এটা যদি আরএনএন সলভ করে, তো আরএনএন এক একটা ওয়ার্ড at a time ওটা প্রসেস করতো, ঠিক আছে? তো তুমি যদি এখানে দেখো এই ইমেজে, প্রথমে ইট ইজ প্রসেসিং what, then time, then is, then it. কিন্তু যত আগে যাচ্ছে সেন্টেন্সের এগিয়ে যাচ্ছে সেন্টেন্সের রাইটের দিকে, ও ভুলে যাচ্ছে যে কোথা থেকে ও স্টার্ট করেছিল। and that's why you see that the dark black color is getting shorter and shorter and shorter as it progresses. তো তুমি ভেবে নাও যে তোমার কাছে যদি অনেক বড় একটা সেন্টেন্স থাকে, যেখানে ভেবে নাও 100টা ওয়ার্ডস রয়েছে, by the time it starts processing the, let's say, 50th word, it will kind of forget whatever it has learned in the first 10 words, right? So this was one of the challenge in RNNs and LSTM based network, because every word was processing one after another from left to right. Okay, so that was one of the challenge, and that's why we call it as a short-term memory loss kind of problem that we had in RNNs and LSTM. Okay, and other problem with challenge, not problem, other challenge with these legacy network was it was not able to figure out the context of a word in a sentence. Like if you look at this word, right? If you look at this word, bat, and if you look at this second sentence, bat. So these are two different sentences, right? This is one sentence and this is another sentence, right? And we have bat here and we have bat here. So in the first sentence, we have the bat flew past my window. So here we are talking about the bat, the animal or the bird, all right? And the other sentence is he hit the basketball with the bat. So here the bat is maybe it's a basketball bat. So it's basically a sport equipment, right? But if you use RNNs and LSTM, the way that it would interpret this bat and this bat would be same. Okay, it won't be able to distinguish between the two different bats contextually. Okay, so these are the few of the problems that we had in LSTM and RNNs. Okay, there were different techniques to overcome that, but now with transformer, all of these were gone. Okay, so I just wanted to give some context about this so that you can appreciate better the use of transformer. Because when someone says this technology is very hot, people are working on this, first thing that we need to learn is why this is so hot and why this is so good. For that, we don't have to learn something which is historical, right? But we should at least know whatever technique that we had in the past, what were their limitations. Okay, if time permits, go over RNNs and LSTM. I can give you some very good resource, and it's very important to learn them so that you get an intuition of what it is and how things have changed over the period of time. Okay, so in 2017, there is a research paper came up called "Attention is All You Need" by the Google Brain team, and that has changed everything. Okay, so this is the research paper. You can search it out in the from the internet. You can download and you can read it. It's a wonderful paper. It's an easy read. Generally, research papers are very difficult to read, but you can always read this. Okay, and the core idea about this attention all you need paper was self-attention. Okay, and this is where we will spend the next 30 minutes. Okay, and if we understand the self-attention mechanism, we are half done. Okay, rest of the things you can pick up of your own. And this has overcome all the limitations that we had in RNNs, and this is one of the state-of-the-art networks that we have today. And this has actually helped us to get new networks like BERT, GPT, and so on. Okay, so BERT is not a completely different network from scratch. It's not like that. It is based on transformer. It was taken from transformer. And today we will just discuss half of the transformer which is needed to understand BERT, and then we will jump into a BERT, and then we will do a demo on SageMaker. Okay, so let's now understand how this transformer works. Okay, so we will understand this with an example so that we can understand the context behind that. So in transformer, we have two blocks. One is the encoder block and another is the decoder block. And in the encoder block, let's take an example of language translation. মানে এখানে আমরা একটা example নিচ্ছি যেখানে আমরা ভেবে নাও language change করতে যাচ্ছি। In this example, we are trying to convert an English sentence into French. Okay, কিংবা এটা যা ইচ্ছা আমরা ভাবতে পারি, এটা বাংলা সেন্টেন্স কে আমরা ফ্রেঞ্চে কনভার্ট করতে চাই। So how we can do this using transformer? So in transformer, what we will do is we will feed the input sentence to the encoder. Okay, and then the encoder will make a better representation of the sentence I am good. That's all what the encoder will do. And after that, this representation will be taken by decoder, and then decoder will translate that to the target sentence. In this case, a French sentence. Okay, so this is all about from the abstract level how encoder looks like. Okay, so just remember this this point that encoder actually gives you a better representation of your input sentence. Now, what is this better representation, how it all works? That is what we are going to see now. Okay, and what we are going to do now is we will zoom in each and every block as we go along. For now, we just have encoder block, right? So let's get inside encoder block and see what we have inside. So if you zoom in inside an encoder block, you will find that it comprises of multiple encoder layers. So this is layer 1, layer 2, like layer 3, and so on. And then we can have n number of layers. Okay. In the original transformer research paper, the author of the research paper used n equal to 6. That means there were 6 encoder layers stacked one after another. Okay. And the way that it used to work is you give the input to the first layer, and then the output of the first layer goes to the input of the second layer, and then second layer's output goes to the third layer, and so on and so forth. And the final representation that comes out of here goes to the decoder, okay, which we have seen in the previous slide. So today we are going to just understand this part. Okay, what happens in this encoder part. And decoder we will not discuss because it's quite a lengthy session, and we have a lot of content to digest. So I just thought to focus only on encoder part, and I'll tell you why we are just focusing on the encoder part. Okay, in some time. Okay, so now we understand we have an encoder block and we have a decoder block in transformer. Within an encoder block, we have multiple layers. Now the question is, how does this encoder layers converts a sentence into a better representation? How it does that, right? So now let's get inside one of these layer, inside one of these layers, because we know that all the layers are identical, all are similar layers, right? But let's get inside one of the layers. So this is how the encoder layer would look like. So within that encoder layer, we have 2 sub layers. Okay, one is multi-head attention and another is feed-forward neural network. Okay, so this is feed-forward neural network, this is multi-head attention. Similarly, the encoder block 2 will also have a multi-head attention layer and a feed-forward neural network, and so on. So if you have stacked 6 encoder layer, this kind of block will be there 6 times. Okay, so I hope that you got the intuition about the composition of the encoder block so far. All right. So now that we learned a bit about this blocks that comprises of encoder layer, now let's understand each of these 2 layers. First is the multi-head attention and another is feed-forward neural network. So to understand how multi-head attention, right? To understand this multi-head attention, we need to understand something called self-attention. Okay, we need to understand self-attention. And once we understand self-attention, multi-head attention is nothing but just like multiples of self-attention. Okay, so let's try to learn what is self-attention. So just focus on this sentence. A dog ate the food because it was hungry. Now we are human, so we understand that here the word "it" actually refers to dog, right? It doesn't refer to food. We as human beings, we know, right? Because we understand the language English, and we know that in a sentence of which word referring to which other word, right? But it is very difficult for the machine to understand this. And how transformer understands that here in this sentence, it refers to dog, not to a food, right? And this is done by self-attention. That means when transformer tries to encode all these words, right, in the sentence, all these words in the sentence, it will somehow from this encoding, it will somehow figure out, the transformer will figure out that this it is more inclined towards dog and less inclined to food and other words like the, it, a, and so on. It is more inclined to this word dog. So this is done by self-attention. Okay, so in transformer, when we talk about self-attention, it's nothing but when given a word, it will try to encode, make a representation of the word, keeping all other words in context. Okay, that means you can imagine that means transformer takes the whole sentence at a time, because to give a context, to learn a context of one word with respect to all other words in the sentence, it has to read all the words together. And this was one of the limitation in RNNs and LSTMs, where it used to read one word at a time, and it used to go from first word to the last word, and it used to forget about the initial words in the sentence. In transformers, it's gone, so that limitation is no longer there, because it reads the whole sentence together, and it tries to encode all the words individually. And when it tries to encode each word, it tries to read all the other words and develop that encoding for that word, right? So that's how in encoder we have self-attention, and due to self-attention, each word always preserves the context of that word with respect to the sentence. Okay, so this is all philosophy, and you understood what what it does, but how exactly this works, right? And this is what we are going to see. So assume that we have this sentence. Okay, I am good. So the first thing that we need to do for any computer, or it's not about machine learning, if you have to process something text, we need to convert into numbers, and that's how any machine learning model will work, right? Because it doesn't understand string or any word as such. So let's assume that we have this sentence, I am good, and we are encoding it with some random number. Okay, these are 3 vectors. So you can just imagine that these 3 words have been encoded with a string of array of numbers. These are random numbers. Okay, so these are not trained numbers. These are just random numbers. Just assume that. And now we make an input matrix. Since our sentence contains 3 words, right? So our input matrix dimension will be 3 by 512. Why 512? Because we just assume that the embedding dimension is 512, right? So it's just like you represent a word using 512 number of array of numbers, which contains 512 numbers. Okay, that's all. So the length of each array is 512. Okay, so this is my input matrix. Now, what we do with this input matrix, we create 3 more matrices called query matrix, key matrix, and value matrix. These are the 3 metrics we create from this input matrix. And how we are creating this? We are creating this using something called weight matrices. So these 3 are randomly generated matrices. Okay, all these numbers are randomly generated, and these randomly generated matrices are learned during the training process. Okay, now how we generate this query, key, and value matrix? We just multiply the input matrix with this WQ matrix to get the Q matrix here. Similarly, we multiply X with WK matrix to get the key matrix. And similarly, for the value matrix, we multiply the input with the WV weight matrix. Okay, so what we are doing, we started with, this was our first step, right? We started with our input sentence, that is our input matrix. And then we multiplied this with 3 randomly generated weight matrices. And then we got this query matrix, key matrix, and value matrix. Okay. Okay, let's go forward and see that why we are doing this. Now, if you look at the first row of all these 3 metrics, you will find that this vector, like this vector, is nothing but the query vector of the word I, right? Similarly, this vector is nothing but the key vector of the word I. Similarly, this is the value vector for the word I, and we have other words as well similarly, right? This is just to give you an intuition where we are going towards. So far, we have not learned, and we don't have any clue why we are doing this. Okay, we will come there. But I just want you to have the notion from where we started and how we are progressing. Okay, we'll come back to that question, why we are doing this. So next, we have to think about it that, okay, we have computed the input metrics and then we generated query, key, and value matrices, but how this is going to help us, right? And this is where self-attention come into picture, right? In self-attention, as we just discussed, that it is a mechanism which relates the word to all the words of a given sentence. That means when you give these 3 words, right, in a sentence, and it tries to find out, this is something which transformer is doing, right, or the encoder block is trying to do. It is trying to make a better representation of this I, right? And how it is doing this, coming up with this better representation, it's going to talk to all the other words embeddings, right? And we are going to see that how it is being done. And since this embedding should have the information of other words, not only this I word, right? It has to have the information about other words. We have computed this query, key, and value matrices. Okay, and now we are going to see how we are doing that. So it's a 4-step process. In the first process, what we essentially do, we just take the query metrics, right? Always remember, we have the input metrics, query metrics, key metrics, and value metrics, right? These 4 matrices we have already. So now in the first step, what we do, we do a dot product between the query metrics and the key metrics. Okay, so now when we do a dot product, we get some resultant metrics like this. Okay, and what this simplifies or what this signifies, when we do dot product between 2 vectors, we actually get the similarity, right? If you, most of you are from machine learning, right? So if you take 2 vectors, right? Let's say this is vector 1, v1, and let's say this is another vector, vector 2, right? So if you see these 2 vectors, v1 and v2, right? The angle between them, if you do this, dot product, the angle between them defines the cosine similarity, right? If these 2 vectors are close enough, then you will see that the theta is less, right? So intuitively, if you think about it, whenever we talk about dot product, we just trying to understand the similarity between 2 words, right? And to give you an better intuition, let's say you have a word called man, okay? And the man vector is this, okay? Let's say this vector determines a man. And let's say there is another vector called woman, okay? So let's say a woman is here. So these 2 are kind of similar, right? So actually in the plot, there will be 2 points like this. This is woman and this is man. I just connected it from the origin 0, 0 and just pointed this, connected these 2 points so that it becomes vector. Now, if you see, if you do a dot product between these 2, you'll find a very high value, right? Because the theta is small. And when the theta is small, that means the cos theta is high, right? If you remember the cos theta, the wave, the cos theta function, it is highest when the theta is 0, right? So if you have 2 vectors, exactly one on top of another, that means those 2 words would be completely similar. It would have a similar meaning, right? So the idea here is we are actually doing a dot product between 2 matrices, which actually give us some intuition about the relationship of each word with respect to other word. Now, if you look at the first, if you look at this resultant matrix that we got from multiplying or doing the dot product between these 2, and if you read the first row, you'll see that the first number represents the dependency of I with respect to I. That is very high, right? And which is obvious because these 2 are, it's exactly the same word. So I should depend on I. And then you'll see that the am is 90 and then good is 80. If you intuitively think, am is also referring to I more than good. So that's why the score is 90 here. So that means I is more inclined towards am and I is little bit less inclined to good. right? So this is how we are trying to get an intuition of each word, how it is related to other words. Okay, so that's the idea behind this dot product. Okay, so in the second step, what we do is we just divide it with the key vectors dimension. Okay, so the dimension that we have in the paper, we use 64. So we just take the square root of that. And this is just for, avoid exploitation of the gradient, because in deep learning or anything in the NLP, we do back propagation, as you know, and we have to make sure that, gradients doesn't blow up. And if you look at in the previous slide, the numbers are very high, right? Although these are randomly generated numbers, but these numbers are very high. So we have to scale it down, right? So that's why we are doing a division with the dimension of the key vector. Okay. Once this is done, in the step 3, we take a softmax of that. Simply, we just pass it through a softmax function. And once you do, go through the softmax function, you see that the summation of the whole vector becomes 1, right? And that's what the softmax does. If you sum it all, you will find it as 1, right? And now, if you read this numbers, it will make some sense. If you read the first vector, you will see that I word is related to itself by 90%. The word I is related to am by 7%, and the word I is related to good by 3%. Right. So we are kind of going what we actually intended for. Right. We are trying to get the context of the word embeddings with respect to other words in the sentence. Right. So once this is all done, the last step is to do the self attention or the build the attention metrics, right? So how we are doing that? If you remember, again, we started with X metrics, query metrics, key metrics, and value metrics. So far, in the first 3 steps, we used all of these 3 matrices, right? Input metrics, we did a dot product with the query metrics, and then we did the normalization with the key metrics, but we have never used this value metrics. Right. So this is where in the 4th step, we are using this. So what we are doing here, we are just multiplying. It's basically the sum of weighted scores. Okay. And I guess I have a example next slide. Yeah. So here, what we do is, if you see, this is my output of the 3rd step, right? This is my output of the 3rd step. And this is the matrix V. So what we do is we actually compute the weighted sum. Okay, how we are doing this? For the first letter I, if you see here, we keep it as like this 0.9, and we multiply this with this whole vector. Okay, and next we take 0.07 and we multiply with this am. Okay, and then we take the last word good, and then we multiply with this vector. Okay, and this is what we are doing. And so intuitively, if you think about it, this 0.9, 0.07, 0.03, this is nothing but these 3 numbers, right? So we are actually summing the value vectors weighted by its score. Okay, and similarly, we will get Z2 and Z3. So this is for the word I, and this is for am, and this is for good. Okay, so that's all what we do in self-attention. Now, if you look at these vectors, right? These vectors have a lot of information about the whole sentence with respect to the vectors that we started with, right? If I just go back.
Shumon, you have a quick question. Yes. Gradient does not blow up. What does it mean?
Yeah, sure. So when we do, I guess we can show it to you. One second. I'll just. I'm just searching for. Okay, softmax function. So this is the softmax function, right? So what happens is, if you have a very huge amount, right? If you have a very a high amount, and that is coming in the output, then what would happen is you will keep on adding that, right? When you do a back propagation, right? And then what will happen is you won't be able to minimize your loss, because all you do in machine learning is you start with some random initialization, right? And then or random initialized weight, and then you progress through the forward pass, and then you predict something, and then you compare that prediction with respect to the actual prediction, not the actual prediction, the actual class level, and then you subtract that using any of the functions that we have, and then you back propagate that. Now, if one of the in one of the layer, if the numbers are very high, right, it might blow up, right? When I say blow up, that means it might, go to a very high number, and you may not be able to, compute. You may not be able to optimize your algorithm to minimize that loss, right? So I'm not finding the. There is a wonderful chart. I'll try to get that maybe towards the end, and I'll show it to you what we mean by that. Because when we think about CNNs or any neural network, gradient might explode. That means it might go to a very high value, so that, and that's why we do a lot of normalization, so that gradient doesn't blow up, right? Otherwise, it would be too much to handle, right? It will take a lot of time to optimize. And the reason that we say this is because if you look at it, let's say if I give you three numbers, okay? So let's say if I give you 100 and just go to that slide and show you. If you just take three numbers, let's say 101,001, and then let's say 20, and let's say 5, right? Now, if you look at these three numbers, this number is completely odd, right? And it might blow up your whole network, because the error that you will get because of this, it will be completely outperformed, by the errors that you will get for these two, right? This will always dominant in your network, right? So if you have assume that this was not that needed. I mean, this optimizing this was not that needed, and so you are actually going in a different path for optimization. So what we do is generally, you can optimize this, and maybe you can scale this data, numbers little down. So let's say it might come down to, let's say, 0.992, and let's say this may be 0.7, and this may be 0.1. I'm just randomly, generating these numbers, but at least now you will have within that scale, right? It will not, grow that fast. Okay, I'll share you one image, and I guess if I can show it to you, then it would have been better to demonstrate. Okay, so all right. So the next is where are we? Yeah. So we have computed the Z metrics, right? And this is what our self-attention is about. Now, what we do is, this is just a recap of what we have done in all these three steps. You don't have to repeat that. And this slide will be given to you, so you can always go over. I mean, it's not that difficult to understand. Now, if you recall, we started with this, right? We have multi-head attention, feed-forward neural network. These are the two blocks that we had. Now, we talked about self-attention, but we did not talk about multi-head attention, right? So multi-head attention is nothing but same self-attention, but just like we have computed the metric Z, we will compute multiples of Z's, like Z1, Z2, Z3, and so on. And why it is needed? Because assume that we have some sentence like this, right? Where the meaning of a particular word is ambiguous. Like here in this word, the it might refer to dog, or it might refer to food. If you use just a single head or only one metric Z, it might capture the information that it refers to a dog more, right? Or it refers to food more. But if you make two more attention heads, right? So you will get more Z matrices, right? Z1, Z2, and so on. So each matrices will give you a different context of the word in the whole sentence. And if you just concatenate all of that information, that would be much more useful for us to interpret, right? So that's the whole idea of multi-head attention. So in a nutshell, multi-head attention is nothing but the same self-attention head, but in place of one Z, we compute multiple Zs. That means we will have multiple query metrics, value metrics, and so on. But it's all same. It's all same, but you have multiples of that. That means during the training, they all will be optimized differently. Okay. So once this is done, what we do is we will just concatenate them. Okay. So once we get all of that, we will just concatenate all of the matrices that we get. Okay. Now, if you remember that we talked about RNNs, that in RNNs we feed the word one after another, right? So that means that in RNNs, the sequence of the word is always maintained. Like if I just say, ami bhalo achi, so এটা যদি RNN কে আমি feed করি, it will first process ami, then bhalo, then achi. So in RNN, when it is processing achi, the word achi, it knows that achi is the third word, right? Whereas in transformers, we don't do that. In transformers, we feed the whole sentence together. So there should be some mechanism where we should be able to tell your transformer that, hey, although we are passing the whole sentence to you, but this is the third word, this is the second word, or we have to pass some information about each word in that sentence. Okay, so this is where positional encoding comes. Okay, so it's the idea of giving some information of each word before we feed that embeddings to the transformer network. And how we do that, if you remember, this is our input matrix, right? What we do is we don't pass that input matrix directly to the encoder layer. We just add one more matrix to that. Okay, and how we come to this matrix we will see next, but we will just add that matrix to this input matrix, and then we just pass this matrix to the encoder layer, to the encoder first layer, because we don't have to do this in each and every layer, right? If you pass this information to the first layer, the first layer's output will go to second layer, right? So that means second layer will already have the information of the encodings of the positions, right? Now the big question is how it generates these embeddings, how this these numbers, like from where these numbers are coming. So if you look at positional encoding, there are different techniques. This is little convoluted, little maths heavy, but I'll try to explain it in simple words. So what we essentially do is you will generate some random sine and cosine waves. Okay, randomly you have to generate, and let's say your dimension, you have 4 dimensions. Okay, just like in the previous example we used 512 dimensions, but just assume that we have just 4 dimensions, because if I have to plot 512 like this, it would be a complete mess, right? So just assume that we have just 4 dimensions. Okay, so we will have 4 different waves. Okay, so maybe 2 sine waves and 2 cosine waves. Okay, just like how we see here. And here in this x-axis, these are the word positions. Okay, now if you look at it, right, let's pick the 30th word. Okay, just let's pick the 30th word. And if you see the 30th word, the embedding would be the amplitude of these waves, 4 different waves. Okay, and if you look at it, the positional encoding of the 30th word would be -1. Why why it is -1? Because that is the first dimension, that is the blue wave, all right? And blue wave is -1, and then -0.25, -0.91, and -0.25 again, right? It's just the amplitude of these 4 waves, all right? These are here we have 2 waves, coinciding in the same point, and then we have another, wave here. So this is how we get the embedding of this 30th word. That means now let's assume that this is the embedding of not the 30th word, but let's say the second word. Just assume, okay? Second word would be somewhere here, right? The embeddings would be a little different, right? The amplitude of this, this, and this, right? Now, this is nothing but this whole vector. Okay, we'll just take that phone numbers, whatever you get, and it will be added here. And then you will just do an addition to this matrix. So essentially what is happening is when you read this encoding, right, of the word am, you automatically know that am is the second word because we have added the positional encoding of the second word with this am. Okay, so this is very important. In fact, in Amazon, if you interview for any of the machine learning position, they will not ask you to implement something, and they will not give you tell you to write a code in PyTorch or TensorFlow, because those things you can always do that. I mean, that is not a big deal, and you will always see documentation and do that. But they might ask you about, okay, positional encoding, it defines the position of each words in the sentence, but how it does that? Okay, so these are the things that people might ask you if you are applying for any machine learning core jobs in general. Okay, so once this is done, now if you just recall, we are almost there. Okay, we started with multi-head attention. We started with the input sentence, and we learned about self-attention and multi-head attention, and then feed-forward neural network, which we have not learned yet. But this is how the input changes, right? We assumed so far that input is going directly to the encoder layer, but now we have just added this positional encoding. Now, the last thing is feed-forward neural network, which is nothing but a dense layer. It's a very simple neural network with a ReLU activation, and it's a complete flat network, and we just add it on top of multi-head attention. So here you will get all these. Sorry, just trying for the pen. 1 second. So here we will pass on these Z matrices, right? And this will go to the feed-forward neural network. Okay. And one other thing that we do is we also have a residual connection, which is an add and norm layer. And what it does is it takes two inputs. If you see, this is one input, there is another input, right? And what it essentially do is it takes the input of the multi-head attention. So if you see this, it is taking one input, this one, and another input, this one. That means it is taking two inputs which were given to a feed-forward network. So this is the input which is given to the feed-forward network, right? And this is the output of the feed-forward network. So it basically takes whatever it is in the below block, but it will also take the input given to that below block. So similarly here, it takes two input, right? One is the output of the multi-head attention and the input which was given to that multi-head attention. Okay, and this is we do for layer normalization so that we can propagate fast, and we the training it can process a little faster. Okay, so this is something. There is a network called ResNet. If you are into CNNs or computer vision, there also we have a residual connection, right? So this is kind of mimicking that. Okay, the idea came from there. Okay, so now we have learned everything, and now if we just stack all those layers that we have learned so far, it would look like this. We have the input, we have the input embeddings, right? This is nothing but, if you remember, the X matrix. Then we added this X plus positional encoding, right? We have learned that how we generate this positional embedding matrix, and then we give it to this self-attention layer. Here we have those three matrices, if you remember, Q matrix, K matrix, and value matrix, and they all build something called Z matrix, right? So attention matrix, right? And we learned that we have multiple Z matrices, and then we concatenate all of them, all right? So we just concatenate all of them. And then we have the add normalization layer and feed-forward layer. And this is what keeps on repeating. So this is just an example of the first encoder. Similarly, we have second encoder, and so on. It keeps on going. And assume that you use 6 such encoders. The output of the sixth encoder, is given to the decoder. Okay, so we will not get into the decoder part, but essentially, if you look at it now, we have a much better representation of this input sentence, right? So that's the crux of this encoder layer. Okay, and if you now look at the decoder part, which I will not cover today, but I have the material in this slide. If you want to go over, you can go over later. It's quite similar to encoder. It also have multiple decoder layers, and within each decoder layer, we have multi-head attention and so on and so forth. But if you look at it, you can do a lot of things only with the encoder, and this is what BERT did. So BERT is basically a special type of transformer which doesn't have this decoder part. Okay, that means a BERT cannot do a machine translation task, right? Like it cannot translate English to Hindi or Hindi to something else, right? It cannot do that kind of task. For those kind of tasks, we should use transformer or other forms of transformer. But BERT can do a lot of other things, like next sentence prediction, or let's say mask language prediction, and so on. And we will see that now, like sentiment analysis and so on, because BERT uses only this representation. Okay, and there is a little difference between how BERT does that, but basically BERT is a special type of transformer which has only the encoder part. It doesn't have the decoder part. Okay, that's all we have. Okay, so next is I was thinking to talk about BERT, but I guess a lot of time I consumed on this. So do you want me to continue for the BERT, or you want me to pause and follow up in the next week? Up to you.
I think you
or
can
if you have any
continue
other
if you have
questions.
time.
Yeah.
I think you can continue if you have time.
Yeah, I have
the
whole I have the whole night, so I can always talk. Okay.
Right, thank you.
Okay, great. So now if you look at BERT, BERT is a special type of transformer, as we just discussed, right? And it also have the same multi-head attention and feed-forward layer, right? And then we have multiple of these encoders. Okay, and I guess there is a typo here. This would be add and norm. Okay, I just copy paste it, add and normalization there, add and normalization. Okay, so exactly like this, whatever we have in transformer. And what it essentially do is, it takes the input sentence. Let's say Python is my favorite language. It gives us a better representation in the form of embeddings, and these embeddings are used in different tasks. So how a BERT is trained. So if you look at BERT in any documentation, you will see that they all will call BERT as a pre-trained model, right? And what do we mean by pre-trained? By pre-training, what they refer to is BERT has been already trained for a couple of tasks, and these are the two different tasks: mask language model and next sentence prediction. Okay, and the idea of these two problems is to make sure that BERT understand that language pretty nicely when it is solving these two problems. So it's like this. যদি ভাবার থাকে এরকম ভাবে ভাবতে পারি আমরা যে BERT কে আমরা আগের থেকেই দুটো টাস্ক দিয়ে দিয়েছি, আর আমরা চাই যে BERT ওই দুটো টাস্ককে খুব ভালো করে কমপ্লিট করুক। কিন্তু কারণ কি, যদি ও ভালো করে কমপ্লিট করে ওই দুটো টাস্ককে, তার মানে ওর ওই ল্যাঙ্গুয়েজের উপরে খুব ভালো একটা হোল্ড চলে আসবে, right? Because at the end of the day, for NLP task, what is needed? The model should understand the language, right? English, Hindi, French, whatever, right? So the idea of these two pre-trained tasks is just to enforce BERT to have a very sophisticated understanding of the language, so that after that, on this pre-trained model, we can fine-tune it to do our task. Okay, and we will see one example now. So imagine that let me first take these two pre-trained model, right? So just assume that we have two sentences: Kolkata is a beautiful city and I love Kolkata. Okay, these are the two cities. Now during the pre-trained time, BERT is supposed to predict this mask word. That means in the first task, what we do is we take the sentence and we mask few of the words. Okay, there is a a maths behind that we mask roughly around 15% of the words in the sentence. But assume that we just striking off this word city. Okay, and what we want the BERT to predict is at the output it should be able to predict that the masked word is city. Okay, that is the first task. And the second task is it need to figure out that the next sentence is actually the sentence immediately after the first sentence. Okay, so given these two sentences, it should also predict that the second sentence either true or false. It's a binary classification, right? True means this is actually the second sentence, or not the second, it is followed by the first sentence, or it is not followed by the first sentence. Okay, so there are two tasks it has to do, right? So this is next sentence prediction is a binary task. It's a binary classification task, right? And the mask word prediction is not a binary classification task. It's a multi classification task, right? Because in our dictionary we might have 30,000 words, right? So every word that is being masked, it needs to predict one of the word from that 30,000 words that it has. Okay, so these are the two tasks it need to do during pre-training phase. Okay, and how it does that? Now, if you look at this BERT layer, we again have the encoder layer, right? All these are multiple encoder layers, just like in transformer. If you remember, we used n equal to 6. Here we are using n equal to 12. Okay, this is something that the author of the BERT paper they have used, but we are free to use 12, 6, or whatever it is. Okay, and now we take two sentences. Now the input sentence is this one, right? Kolkata is a beautiful city, and I love Kolkata. Now, if you look at it, we have to mask that city word, right? And how we do that? We add a special token called mask. Okay, and we also need to specify that the second sentence starts when. So that's why we kept another new token called SCP. These are special tokens. These are the tokens that been defined. Okay, so in the code you will see that if you print that vector, you will actually see masks and SCP. These are the tokens that have been used. Okay, so SCP token is used to separate two sentences, and mask is used to mask one particular word in that sentence. Okay, and one more thing that it does is it adds a special token called CLS at the very beginning of the first sentence. Okay, so this is how the input is fed into the first layer. This is how the input is fed to the first layer during the pre-training task. Okay, now there are few embeddings that are being used. One is segment embedding, and segment embedding just defines that which are the tokens that are part of the first sentence and which are the tokens are part of the second sentence. So if you see, the embeddings are all EA, right? All EA. And the reason all of them are EA is because we know that this particular sentence, all the words in this particular sentence from here to here, okay, let me just delete all of that. From here to here are part of sentence A, right? First sentence. And everything from here to here are part of sentence B. Okay, it's actually not here, it's actually till here. Okay, so this is just the segment embedding is just defines a segmentation between two sentences, and token embedding is just the token embedding, just like we have seen how we generate embedding for the input token, and in BERT we use a special embeddings, and then we have the positional encoding, and positional encoding is the same that what we have discussed before, right? So we can always add that, and at the end we add all of these three embeddings and then feed the input to this encoding layer. Okay, now a lot of things happen. Now if you see this particular sentence, Kolkata, okay, I just missed one important thing, sorry. Now what happens is, once you feed this to the input layer, it keep on going from encoding layer 1, 2, 3, 4, and so on, right? And the output that you get, right, that is a better representation of your input tokens. Okay, and this also, if you see, this also predicts, right? This also predicts whether this mask word is city or whatever it is. Okay, and one key thing to remember is now all of these embeddings, right, have a context of the whole sentence, right? So now if you look at, now we can use this representation on the top. We can use this representation on the top to solve some problem. And let's try to solve one of the problem. And that is, let's say, sentiment analysis. So let's say this is a given sentence. Suman loves Kolkata. So now we are doing a fine tuning. Okay, whatever we have done before is pre-trained. That means these are already done by BERT, by libraries like Hugging Face and various other companies, and they have already pre-trained that. You can just import and use it. And this is what we are going to use in SageMaker. And next, what you can do is you can just fine tune this model. Okay, so we will just use the representation of this input sentence to solve our problem. And let's say we are trying to solve sentiment analysis. And this is the input sentence, Suman loves Kolkata. Okay, and now if you look at this embeddings, we don't have to use the representation of all these words. We don't have to use. All we have to use is the representation of the first token, CLS. Okay, you may ask why we want to use the token, representation of CLS token. Why not Suman, Kolkata, or SEP? Why can't we take all of them? The reason is it is not needed, because a sentiment analysis is a binary classification, right? It can be a positive sentiment or a negative sentiment, right? And we know that CLS token comprises of all the information of all the words, right? And this is how self-attention works. So we know that CLS can be used as the representation of the whole sentence. All we have to do is we have to create our own softmax function and a feedforward neural network, and we can have a binary classifier at the output, right? That's all. Similarly, if you take another example of name entity recognition, there we can again give the same sentence, but in this case we don't need the representation of CLS, because name entity recognition, what it does, it tells you each and every word, whether it's a person or a location or whatever, right? So we have to put some classifier and with some softmax, some activation unit, and then it can predict whether each and every word is contains some entity or not, like person or location or so on and so forth, right? But the idea that to understand from here is we are just using the representation. Okay, we are just using this representation, and what we are extra doing is we are doing this fine tuning in the top. Okay, so this is about a BERT, how a BERT works. Okay, and now I have a demo, but I guess it's if you are fine, then I can go ahead with the demo.
Please.
Okay. All right. So here's the demo for we are going to use BERT, and we are going to take a data set from Kaggle. And in fact, this was there recently, I guess last year itself. And the idea is we get lots of tweets, right? And we have to figure out that tweet contains a disastrous tweet or it's a normal tweet. Because a lot of time it happens, right? We are in the street, we saw an accident, we just tweet that, hey, I just saw this accident, can anyone help? So if the nearest fire brigade or police station come to know about that problem with the location, they can come and rescue, right? So the idea is, given a tweet, we need to identify whether that tweet is a disastrous tweet or a normal tweet, just a regular tweet. So if you think about it, this is very much similar to sentiment analysis, right? Because it's also a binary classifier. So let's see how we can do this. So first, this is a Jupyter notebook and SageMaker, right? You can always use Studio or anything of your choice. But the first thing that we need to do is we need to install Transformer, because we are going to use Hugging Face library for this, and all those pre-trained model are implemented, available in that module itself. Okay, so we are just installing it. And once this is installed, we can import a few of the libraries like NumPy, Pandas, because we are going to, play with the data set. And we are creating a bucket, and this is the bucket we are going to use to save the data set and also the model artifacts. And then, we will also use prefix. So prefix is, how many of you are aware of S3 bucket and all of that? Can you say yes, no in the chat?
We heard about,
Okay.
learned about S3 bucket, but I haven't practiced.
Okay, perfect. So you can think about S3 as a storage dumping area where we can just dump our data. Okay, it's a object-based storage from AWS where you can store the data and you can access that data from any services. Okay, it's one of the oldest service that we have in AWS. So bucket is nothing but you can think about it as a folder, although it is not a folder, but you can think about it as a folder. And a prefix is maybe subfolders, because we may use the same buckets for many other projects, right? So that's why we kept a prefix, and we are going to use this later on, okay? Because we are going to upload the data in that S3 bucket. And next is we are creating a SageMaker role. So SageMaker is the service that we are going to use for training. We are not going to train that model in this Jupyter notebook, okay? So we are going to train it in SageMaker. And to use SageMaker need to have the access to S3 bucket, because I am going to put the training data set in our bucket. So SageMaker should be able to talk to S3 bucket, and it need to have that execution role. And that's why we are just granting that role using this particular function bucket. Okay, so I already downloaded the data in this particular notebook, and it's there under dataset raw data.csv. The repository is there in the GitHub. You can play around and do whatever you want. Okay, so I'm just loading this dataset using Pandas, and there are a lot of columns in the dataset, but we are interested in only 2 columns: a label and sentence. And if you now print this, you will find the label is either 1 or 0. Okay, we are just printing the last, 5 tweets, but you can get the idea, right? So again, we are just printing the sentences. And now if you see the sentences, you will see that a lot of tweets contains hashtag, some HTTP link, which is quite natural, right? When we tweet like that. So let's do some cleaning. So there are some wrapper functions. I'll not go over that because it's pretty straightforward. We'll just remove some punctuation mark, HTML tags, and emojis, and so on. Okay, and then if you just remove them, so I'm just using the data frame and the apply method, where you can just pass on these wrapper functions, right? It will go over all the tweets, for all these functions. And now if you print this, you will get a much cleaner data, right? Okay, so now this is done. The first thing we need to do for machine learning in general is we try to see that the data set is balanced or not, right? Because we are trying to solve a disaster versus non-disaster tweet. So we need to make sure that we have enough data of both the classes. So it looks like we have quite a decent segregation of 57% non-disaster tweet and 42% disastrous tweet, right? So next thing, what we do is we are just trying to understand what is the length of each sentence, just to get an idea about the data set that we have. And if you see that the maximum number of word count is roughly around 15, 17. And this is needed because this is something that we will use later on while training the model. Because in the BERT model, if you remember, if I just go back here, we feed this sentence, right? So we need to, it would be good that to have an idea about how many words that we have in the sentence, so that we can feed that, okay, in the model. So just for that reason, we are just doing a word count. And next thing is we have to split the data for training and testing. And we are using the scikit-learn's test and train split. And we are just splitting it, okay? And this is for how we split the data set. We pass the data frame and call this train test split, and it returns the 2 sets. Okay, so by default, it splits with 75% training and 25% test. But if you want to have 30% of test, you can always add using this test size parameter, right? You can just give a test size here. Yeah, I mean, I'm very sure that you all know this. Okay, so whatever you want. And then once that is done, we are just saving that training and test data set into a CSV file. And finally, we have to upload that file into S3, right? And this is where we are using that bucket and prefix which we have declared before. So we are just uploading into our S3 bucket in two separate files: train.csv and test.csv. Okay, so now we are done with the just data exploration and data splitting and uploading to the S3. Now comes the training part. So a lot of you have used in SageMaker, as I see in the chat. But if you're new to SageMaker, how SageMaker works is, this is the notebook that I am in, right? So you can imagine that this is just a Jupyter notebook in your laptop or anywhere, right? Although it is in cloud, but just assume that it is in some machine. Now, training doesn't happen in this machine. Training will happen in some other place. Okay, and that other place is actually a container. Okay, it's a Docker container, and we can actually tell SageMaker that I need to run a PyTorch model, or I need to train a PyTorch model. So SageMaker will pick the right container image from its repository, which is stored in a repository called ECR, Elastic Container Registry. It's just like Docker Hub, but this is within AWS. Okay, and it pulls that image, it creates a container for us, and there it does the training. And that container have the access to all the S3 bucket locations that you have provided and all of that. And once the training is done, it will just destroy that infrastructure for you, so that you don't have to spend a lot of money on GPUs and CPUs while the training is not running. Okay, so that's why SageMaker is very optimized, and it's very efficient for us to train our model and deploy that. Okay, so similarly, once the training is done, right? So once a training is done, it will, before it destroys that container, it will save that model artifacts and all the required files into S3. Okay, that location also you have to provide, or it can use its default location. So it will read the data from S3, it will do the training, and it will send the trained model in some place, and then it will just get destroyed. Okay, so that's the beauty of a SageMaker. And once that is done, we have to deploy that model, right? Because what is the point of only training? We have to deploy. So while deploying, again, we create a container, and there it takes the model from S3 bucket and it gets deployed. Okay, so we are going to see that in action now. So we are going to use a helper function for this. So you can you can write your own code. You don't have to write a separate code for SageMaker. If you have written a code, you can always reuse that. It's only that during the training process, you have to say that, hey, SageMaker, pick up a container which has PyTorch, and take my code and use this code while training. Okay, that's how you can feed your code to SageMaker. So we are going to use this train_deploy.py file for training, and it has a lot of things, but I'll just pick up a few of the important things. One is the maximum length, right? So we are going to use 64 as the max length of any sentence. And if you see that we have imported transformer, and this is the package that we have installed, right? And it has BERT model. So this is the BERT pre-trained model. Since this is a classification problem, we are going to use BERT for sequence classification. Okay, so there are a lot of different models available in Transformer. You can check the website and documentation, and you can pick the right one. Okay, and BERT uses a special tokenizer, and that's why we are importing BERT tokenizer. So tokenizer is nothing but how to where it just adds the CLS token and the mask token and all of that, right? We have seen that. So all of these happens here. Okay, so important thing to show you is how it does that fine tuning, right? So if you come here under training function, okay, in this under this training function, here is the model definition. Okay, and if you see here, we are saying that use the pre-trained model, and BERT has a lot of pre-trained model. One of them is BERT base uncased. Base means it has been pre-trained with 12 layers. There is also a BERT large, which contains 24 such layers. Okay, so again, to give you a context, BERT base is like this. So during the pre-training phase, this is the pre-training phase, right? Here we have shown 12 layers. So when you pick BERT base, right, it will be you are sure that it has been trained with 12 such layers. Okay, so we are using a BERT base, and uncased means this has been trained with a corpus of data which are not case sensitive. So even if you send a text saying Suman as S capital and some other text as Suman as S small, it will not differentiate. Okay, so there is a BERT model which is case sensitive, that is also there, but we just use a BERT base uncased. Okay, and then we are just saying how many labels that we want for our problem. Our model needs 2 labels, right? Because this is exactly this model, right? Either positive or negative, right? Either disasters, it is a disastrous tweet or it's not a disastrous tweet. So this is what we are telling, that this is the number of class labels that we want. And there are a few other things that we are passing, like output of hidden states, output of attentions, and so on. So output of attention states are like is this. If you see this transformer, BERT model, we are interested always in this top layer representation, right? But at times there are problems where you might want to see what is the output of encoder layer 1, what is the output of encoder layer 2, right? In those cases, you can use output hidden state as true, so that while the training is done, you can also read the output of all those embedding encoding layers. Okay, so for this problem, we don't want this, but it is always possible. It's not a black box. You can read the output of each and every layer if you wish to. Okay, so that's about the training part. Okay, and then if I just come down, now we have to start the training, and this is how the training works. As I mentioned, we can define what type of what is the framework that we are using. In our case, we are using PyTorch, but it can be TensorFlow or anything, right? And what we do is we will create something called an estimator object. Okay, and here how that estimator works is this: you import SageMaker from PyTorch. Okay, SageMaker.PyTorch, and there is a class called PyTorch, and we will just use that PyTorch to create an estimator. Okay, so estimator is nothing but an object which will help you to create that container for your training on SageMaker. Okay, so here you can define everything, like what should be the entry point. Entry point should be the script that we have just walked through, right? Some part of it. So we are saying that, hey, create a PyTorch container, okay, which has all the binaries libraries of PyTorch, and start this code. And where this code is available, I can define that what is my source directory, right? So I know that this is there under the source code folder. I'm just telling SageMaker about this. You can also define the framework version, PyTorch Python version, and so on. And also you can say how many instances you want to start your training. So if you say 20, that means there will be 20 containers or 20 instances basically, which will be initiated, and they all will be used for the training. So this is what distributed training is about. And we say that it's very easy with SageMaker, right? Imagine that you have to do this of your own in your on-premise or in your own data center. It's very, very difficult to even distribute the training, even if you have those many number of hardwares. Okay, so here we don't have to worry about all of that. And then we can define what type of instance that we want. It depends about your problem statement or how many GPU, CPU, and all of that you need. You can define that, and then you can also define some of the hyperparameters. Once this is done, okay, you call this fit method, and the moment you call the fit method, you will be passed, you need to pass the input data and the testing data. And then the actual training starts. Okay. So the moment you call this fit, if you see this image, it creates that container and it reads the data from your S3 bucket and it starts the training. Okay. So now if you look at this training, it has a quite a verbose output, but at the bottom, if you see, you will see that the training time is roughly around 600 seconds, so roughly around 10 minutes. And after this 10 minutes, that container is gone. So the container is no longer there. So you are not charged about that, right? So the last thing is we have to deploy that model, right? So for deploy, what we can do is we can just use estimator.deploy and the number of instances that we want for the deployment and what type of instance we have. Okay. And once this is done, you can serialize the predictor object, and then we can do the prediction. But before we do the prediction, I want to show you one thing on the deploy. How it is able to deploy is because we have written this functions like function fn and input fn in that script. So if I just scroll up, and if you just see this predict method, the model fn function, you will see that we are loading that function. We are loading that model from S3 because this has been already pre-trained, right? If you remember previously when we started the training, we used that BERT-based model. But now for inference, we are using our model, which we have already trained, right? And this is the directory where this is nothing but that S3 directory location where our model artifact is saved. Okay, so we are just taking that model from there, and then we are just doing the prediction. We are just calling that model with an eval so that we don't do a back propagation, right? So once that is done, we just print the output. Okay, and we are going to see that how we print the output. Okay, so let's come back here, and here let's try to test our prediction or our model, right? So I just created a small dictionary so that we don't see this numbers as output 0 and 1. We actually see real disaster or not a real disaster. So assume that we have 3 sentences. Okay, I met my friend today by accident. See this, we have a word called accident, but this is actually not a disastrous tweet, right? I just made this intentionally so that we can actually understand how powerful BERT is, right? So now if you just call this predict method on this predictor object with all those sentences and print out the labels, you will see that I met my friend today by accident is not a disastrous tweet. That means it's not just encoding accident as a negative word and as a disastrous word, and it is just flagging it that this whole tweet is a disaster. That is not the case, right? And if you see the second sentence, Frank had a severe head injury after the car accident last month. So this is a real disaster, right? And again, there is another sentence, just happened a terrible car crash. So this is also a disaster story. So you can try it out. You can put different sentences and see how it works. Although this whole training was done with a small set of data set, roughly around 10,000 tweets. So it may not perform that well. In fact, one more thing I missed out to tell you is in the logs, you can actually see the test accuracy. So if you see the test accuracy is roughly around 78%, which is not all that great, but it is quite decent considering the amount of training data set that we had. And we did not do any tuning on the BERT side, right? We just used it. We are not doing any hyperparameter tuning and so on and so forth, right? So that's all about it. Once you play around this, and always remember this, I tell everyone, because I also keep my model hosted without using it, and I get charged. So always remember to delete that endpoint so that it gets deleted. Okay, so that's all about it. I guess I took a lot of time, but if you have any questions around this now or later, feel free to ask. I'll be very much happy to help you. I guess I will share this GitHub link. Okay, so I'll just post it here right away. I guess it's before I forget, and then we can call it a day. So I guess this is the GitHub repo.